our first speaker. It's my delight and privilege actually to welcome our first speaker. And if you look at all our backgrounds, we thought that we were being pretty cool about putting all these, bright backgrounds. But Asitang beats us hands down with the kind that he has because of where he's coming from. And we're so delighted that he's here. I wanted to, before introducing him, I wanted to say something that a few years ago, there was a poll done about, what was the most abused and overused idiom in the world? And the answer was, it's not rocket science. And when we look at Asitang's background, actually for him, it's not just rocket science, but also data science. So he is with rocket scientists dealing with data science. And I was watching his TED talk, which you all should watch. It's called Demystifying Data Science, I think. Yeah, Demystifying Data Science is TED talk. I was watching it at 4:30 in the morning today. And there's an anecdote in there, which with his permission, I'm using, that he was trying to explain to his Uber driver what he really does. And by the end of it, I mean, imagine making an Uber driver get lost. And that's what he did, because the Uber driver was completely lost by the time he was finished explaining what all he does. Asitang is a principal data scientist at NASA's Jet Propulsion Laboratory. He spent the last 8 years developing machine learning solutions for NASA JPL and working on providing ML expertise on JPL collaborations with DARPA, the Department of Homeland Security, the National Cancer Institute, the United States Geological Survey, and others. He loves creating and working with algorithms and techniques involving graph theory, NLP, and information retrieval, among other things, and also loves dabbling in creating interactive visualizations. In his free time, he loves to spend time cooking. Wonder how he has all that free time though. So he likes to cook, doing nature photography and reading fiction. And as I said, do watch his TED Talk, Demystifying Data Science, to know more about his work and data science in general. Over to you, Asitang. We're so pleased that you're here today. And you're going to be talking about the 5 data scientists you meet in heaven. Over to you, all yours.
Thank you very much. It's a delight to be here, and thank you, Preeti, for that introduction. And so, yeah, I'm going to be sharing my screen. Let's see, should work. Okay, let me know if you guys all see the first screen of my presentation. So the 5-ish data scientists you meet in heaven. Again, it's because of my love for fiction. There exists a book that has a similar name called The 5 People You Meet in Heaven. I've not read the book, but I was aware of the title, and so I thought, why not? So this is what I'm going to be talking about. Hi, hello everyone. I'm Asitang Mishra. I'm from NASA JPL, where I work there, not from there. But and I live in Los Angeles most of my time, and also we are going to be talking about, so before you meet those data scientists in heaven, a little bit journey before that. Now, what are we going to talk about today? Let's see. We're going to talk about my education, what I studied. We're going to then talk about the work that I do or have done, and let's see. Yeah, and then finally, we're going to talk about some commonly found data scientists in nature. And so, without further ado, let's begin. So yeah, so as some of you might have already guessed, I studied in India. I did my undergrad in India in electronics and communication. And but after 4 years of college and mostly I think I got into electronics because my dad is an electronics engineer, so it was pretty interesting to me. It was kind of a no-brainer. So after 4 years of college in India, I realized that a lot of my knowledge was very bookish, and I had hardly any practical knowledge at that point. So like any smart engineer or in India, what I did was I became a software engineer at that. And once I was a software engineer, I decided that I would go and do my master's somewhere. And it happened to be University of Southern California, VITERBI School of Engineering, in the Department of Computer Science. So I did my master in computer science in the general track. It was not a specialization, but during my master's studies, I came across this subject called NLP, which is known as natural language processing, that was very interesting to me. And as I've already told all of you, that I'm very interested in reading fiction, so I was also very interested in literature. So I thought that it's a very interesting field because it merges linguistics and computer science, and it also has AI and machine learning in it. So I tried it out. I took some courses in applied natural language processing, and I loved it. I did some research with a few professors there as well, and soon I found myself working at NASA Jet Propulsion Lab as an intern. Now I did 2 internships there before being offered a full-time position as a scientific application software engineer. It's quite a mouthful. Most of the times when people would ask, what's your role at NASA? I would be like, it's something software, something application engineer. It's a pretty long one, but I make software. I think 1 year in, my bosses saw that the work that I was doing was very machine learning, NLP heavy. So my role got switched to a data scientist at that point. And since then, I've been a data scientist mostly. And so this basically was my not so straightforward journey to becoming a data scientist. Then let's talk about JPL. So as I think most of you already have guessed and know and have heard that it's NASA. Now, as a lot of you don't know, it is also Caltech, or California Institute of Technology. It's super interesting because NASA is it's a government agency, whereas Caltech is a private university, and together they make this lab called Jet Propulsion Lab. The history is that JPL was a lab of Caltech that was experimenting with propulsion technologies back in the day, and they have a separate campus though, when NASA first came to be, JPL was offered to become a NASA center, and obviously they accepted, but California Institute of Technology didn't want to let it go. So they decided that it will be a NASA center, but it will be managed by Caltech, thereby giving birth to this very unique institution where I work today, JPL. Now, they have a name for it. It is called Federally Funded Research and Development Center. And fun fact, it's the first NASA center, actually, out of, I think, don't know, maybe 13. At some point there were 13, I don't know, more or less at this point. So yeah, so that's JPL. And JPL was the first NASA center, or JPL worked on the first satellite that America sent called Explorer 1. But more recently, JPL, in recent times, it has been in news for sending robots to Mars, or Mars rovers and Mars landers and whatnot. So it doesn't work on propulsion technologies as much or at all these days, but it has switched gears to working more on robotics at this point. But the name stuck, and we are still called Jet Propulsion Lab. So it's kind of a little bit of a history of JPL. So, but although we do a lot of robotics and a bunch of space stuff, but my first project when I started working at JPL was none of those. It was not at all related to space that's in the sky, but it was related to a different type of space. It was related to the internet. And the project was called MEMEX. Now, what is MEMEX? So it was a DARPA project that basically wanted to shed some light on the deep and dark web. Now, deep web is the part of the internet that's considered, some say it's 96% of the web, some say it's 70%, but everyone agrees it's a big part of the web that we usually don't interact with. So when you Google, when you use Bing or any other search engine, you only see a small part of the internet, because those are that's the part of the internet that they have crawled and indexed and make it available to you. So you can basically search those pages, but a big part of the internet you never really see. And neither these companies like Google and others, maybe they don't care about it because maybe it's not commercially useful for them. But it's super useful for the government, and maybe it's also not maybe, but it is actually very, very useful for researchers as well. Now, the government, what's the interest of the government in this part of the web? So there's a small, I mean, maybe small, yeah. Let's just say there's a part of the deep web that's called dark web. There's illegal activities going on. Now the government wanted to shed some light there, and I see someone raising their hands. I'll probably answer questions in the end. But so the government wanted to shed some light on that, and to show their goodwill, DARPA, which a lot of times does projects that are not very public facing, they wanted to make all the technologies as part of the project available to the public, which is true, because whatever we developed as part of this project is still available to the project, to the public, as like the data we got, the technologies we developed, everything is open source. But it was a very unique project, and that we were working at that point. So because I think a lot of people on this talk are data scientists, I want to kind of, with each project that I describe, I'll also tell you about, as a data scientist, what is it that you do in that project? What do you expect to do in a project like this? So let's see. So what we did for this project was we built search engines, and not just search engines, but we wanted to understand how machine learning and AI can be married to search engine technology. How can we use machine learning and AI to make search engines better? Also, we did crawling. A lot of people know crawling as scraping as well. There's slight differences, but let's just say they're same for all this, like, our purposes. And so we wanted to understand how machine learning AI can help in crawling as well, how they can focus the crawler, because obviously we did not have the resources to crawl the whole of the internet. We wanted to be really smart about it. So we wanted technologies which we can focus more on towards those topics that we wanted to find on the deep web or the dark web. Someone is trying to request control of my screen. Probably should not. Okay. Okay, so then obviously storage. Once you have a lot of data, so even if you scrape a tiny bit of the internet, you still get a lot of data. And how do you store that data? So creating solutions that can store that amount of data. And once you have that amount of data, you want to build these systems that can retrieve that data. So basically, you create indexes. The kind of data we gathered was images, videos, and text predominantly. So we wanted to index it in a way that we can retrieve it pretty fast, and we can run extraction pipelines and other things on that. So it was a very, very interesting project. A lot of teams were working on it. At one point, 20 teams were working on it, which consisted mostly of the top universities of US, like Stanford, MIT, Georgetown, USC, UCLA. There's CMU, and some private industry, some startups, and some government agencies were also part of this project. So it was, all in all, I was new to the project, and it was a lot of fun, a lot of learning, and it was very challenging at the same time. So let's see another project. It's called LabCAS, or Laboratory Catalog and Archive System. Now, LabCAS is another interesting project. It's still going on, and it's related to cancer research, specifically biomarker research in cancer research. And so in this system, we are trying to develop an archive system. We have already developed it, but we're trying to perfect it. The project has been going on for more than a decade at this point. And the basic idea is to create an archive system that can store a lot of data products that come out of cancer research and cancer biomarker research. You would think, why would a space company or a company dealing with planetary data, planetary missions, they want to be part of cancer research? And I think the answer is that the kind of data that we deal with, especially the images, are not very. Sometimes you're looking at the image like a sky survey of, and it kind of looks like the human body, the pictures of human cells and tissues and things like that. There's a lot of similarities when it comes to machine learning and AI. The models for one could be used and trained to develop predictive models for the other. There's a lot of overlap in terms of machine learning and AI, but I think the real reason was probably someone was giving a talk at some point of PDS, or planetary data systems, which is an archive system that NASA uses to store all the data that it has collected over the years in its planetary missions. And it is peer-reviewed. It's easily accessible. It's a really good technology. So someone probably was presenting it at a conference, and in the audience there was someone who was in the medical field, and they said, "Oh, we want that as well for our field. Can you do that?" And someone probably at JPL said, "Yes, we can do that." And so that was probably more than 10 years ago. And so this is one of the projects that I'm working on at this point, and we have more than 40 American research institutes and hospitals that are part of it. We are collecting data from it. We are trying to help them homogenize all their data, give it to us so that we can put it in our archive system, where we make it available to all the researchers who can obviously then do their research on the data, publish paper, publish their studies and things like that. So kind of one central repository of all this kind of data. So another very interesting but very different project from the previous one. So what does this data scientist do here? So obviously building in storage and retrieval solutions. And the data is very different from the internet data, but there's a lot of overlap in terms of building a storage and retrieval solution here as well. Then obviously designing the data cleaning and the processing pipelines, which is very important here, because in your day-to-day, you have to deal with a lot of data from different sources. So you need to homogenize a large amount of data and maintain its storage. So, yeah. Third project. So Zwicky Transient Facility, is the name of a project which has installed a high-resolution camera at the Austrian telescope, Austrian Samuel telescope, and it's at Palomar Observatory. It was installed in 2017, and so what it enables astronomers is that now they can do time domain astronomy, which basically is the study of transients or astronomical bodies which change with time, or their light changes with time, and which is like, for example, supernova or pulsar or any variable star for that matter. This is kind of a picture of the Palomar Observatory where this camera is installed. And so once this camera was installed, it started generating a huge amount of data, terabytes of data at that point of optical sky survey with a cadence of 2 days, which means that every 2 days it would cover the whole northern hemisphere. And that basically enables this cadence of 2 days enables scientists to study transient properties of stars and galaxies and other astronomical bodies. There's a kind of a picture of what we would deal with Here you can see a variable star, the light from the variable star in the center, how it changes with different times when the picture was taken. And here there's a good animation that shows how like a pulsar can generate something called a light curve. So once you have these light curves over a period of time for a particular star, particular variable star, or any point source, you can do a lot of different types of machine learning and AI on top of that, and a lot of predictive analysis on top of that. And specifically the project that I was dealing with wanted to classify these variable stars into these different categories. So yeah. So let's see what a data scientist can really do in a project like this, or at least what I did. Researching the state-of-art classification models. So you don't always want to create something from scratch that, something completely new. You probably want to research what's already out there. Can you really use it? You want to spend your time, or you want to spend your time building something completely new. And then obviously you have to build something for the data that's at hand. Maybe even if you're using a model that already exists, you want to retrain it or fine tune it on your own data. So that's something that you need to do. And also since there's a huge volume of data involved in this kind of a project, so there's a lot of processing that needs to happen in real time for these systems. So you have to have pipelines, really robust pipelines that can process really high volume of data in astronomy. So these are some of the things that where the data scientists can really focus in a project like this. Now the final one, and it's a very exciting one because it's going on at this moment, and it's at some point United States realized it actually declared 50 minerals to be really critical for the national security, and they asked people from United States Geological Survey to do the critical mineral survey, and USGS told them, sorry, we'll need 50 or 500 years, something crazy like that, to do that, because the process is very, very manual, and so it's very time taking. So at that point, the government put DARPA into this project and said, what can we do to make the time less? What can we do to have this critical mineral assessment faster? And so at that point, NASA and some other agencies were involved in this project. And so we all start thinking, so what can we really do? How can we really automate everything that is needed to do a geological survey? What are the different elements? So for that, we needed to understand what it is that USGS does to do a mineral survey. It was again a very exciting project and very interesting one. And at that point, we said, okay, let's create a challenge. Let's see what people come up with. But even to create a challenge, it's not a very easy thing. You have to understand what is it the problem that someone can solve, how is it going to be useful for us, and even understanding the flow of USGS was a very challenging for us, because as you know, we work with JPL, and USGS worked with a entirely different type of domain. So it was difficult, but really, really interesting. So again, we came up with two challenges. The first one is called Map Georeferencing Challenge. And here we give the participants a large, some amount of scanned maps. And we want them to place those maps exactly, or geolocate them or georeference them and put them exactly on the globe at the right place where they belong, as in this picture. The next challenge is called the feature extraction challenge. So this is again a very interesting one, where as humans, it's very easy for us to read the legend or a description of a map and then find those features and the legends in the map. But for machines, it's apparently a very difficult task for some types of features. So in this challenge, we are giving our participants the legend features, and we're asking them, can you really find those features in the whole map that you see in the legend? This project, I think in the last week, the registration either closed or is still open for this one. But this is the second project. So all in all, initially we wanted to kind of have only 2 challenges. Maybe in the future we'll have more, but yeah. So what does a data scientist do here? Again, a little bit different from the previous projects. You have to design and define the technical challenge itself, how big the challenge should be, how small the challenge should be. Like for example, in the legend, the feature extraction challenge, do you also want the participants to detect the legend itself, or do you give the legend to them and say, detect the feature which is in the legend? So what part of the technical challenge you want the participants to solve, how much you want them to solve, how less do you want to, how big you want to make the challenge, how atomic you want to make the challenge. So these are all the questions you think about when you're designing or you're defining the technical challenge itself. We came up with like 10 AI ML challenges, and then in the end we settled on 2 of them. So you can see it's a challenge in itself to come up with these challenges. Then once you have a challenge, what's the success criteria? What's the scoring metric? A lot of times you get lucky, like the first challenge in the georeferencing one, you get something really standard like RMSE score not to go too much into technical bits. There's something called RMSE score that exists, which you can like directly use in this kind of a machine learning challenge or a machine learning problem. But for the feature extraction one, no scoring metric really kind of existed that was de facto and we could have used. So we had to come up with an entirely new set of implementation and a design for that scoring metric that we are using to find the winners. Then building data preparation and evaluation pipelines. So again, some workflow that will actually do the automation for scoring once you have the result, the predictions from the participants. And last but not the least, and I feel like this is the most important thing that we did as part of this challenge, is annotating a lot of data, like basically generating and sometimes manually creating a lot of like tagged data sets so that the performers can actually train their models on it. Often overlooked, but I think it's one of the very important part of doing machine learning, to actually have some data to learn from, and when you don't, somehow generating. So again, a very interesting project. You can follow it, you can Google about it, and it will give you all the information. Okay, so this brings us to the third section of this talk, where I'm going to be talking about the data scientist commonly found in nature. It's going to be short and simple. Hope you guys enjoy it. And these are also the kind of data scientists I have personally found in my career. So the first one, I call them business tycoon. They love charts. They love using tools like Power BI, Tableau. They love SQL. A lot of them have not heard about key value storage or any other type of storage. They love SQL so much. They might even use R if they're too savvy, if they feel like they're using too much tools and not doing enough coding. They get really excited about no-code, fully managed cloud-based ML solutions that are provided by a lot of big companies these days, like Amazon, Microsoft. Almost all big companies have some sort of a cloud solution where you don't have to do coding, or you don't have to do machine learning. You don't have to be like a machine learning specialist or anything. That you can just train your model by giving it data. So this kind of data scientist loves these kind of products. Second is the deep tinker. They love tinkering. They love tinkering on the deep neural net models. They use words like TensorFlow, PyTorch, and they love making all sorts of complicated architectures in deep neural nets. the cool thing about them is that they know all the tricks and tips to make a neural net actually work, which is not always the easiest thing. Or in the past, it used to be even more difficult to make a neural net actually produce something useful. But these days, getting more and more easier. But still, yeah, you need to kind of know all the tips and tricks and how to make it work. So I call them the deep tinker. The Cinderella. So these are the kind of data scientists. They love getting into rabbit holes, and they keep on banging on the same problem over and over again. They love beating on a dead horse, and it just goes on for days and days. And they would not come up with any solution for a problem, but they would actually generate way more questions and way more problems that they need to solve. They're very researchy. They're more leaning towards core research than applications sometimes. They sometimes maintain a notebook of ununderstandable figures, which are often only understandable to them. And sometimes they even forget what they were trying to write. So we call them the Cinderella. The librarian, the fourth kind, is they know everything about the latest and greatest libraries and tools, all Python libraries, Java libraries, and anything that's new that could be used. So they would know about it. They also, and the good thing is that they love to contribute to open source as well. So the amount of libraries sometimes they use, they also contribute back to those libraries. It's great. The publisher. Okay, so it's an interesting one. They love publishing papers and they love presenting their work above all. Sometimes they love it even more than actually doing the work. So they're usually a lot of times the face of a team, of an organization, but still they're data scientists in every right. And the last but not the least, and that's why I said five-ish, because the sixth one, and to be honest, this is my favorite kind of data scientist, is I call it the pirate, because they get the job done. So you get them the job, and somehow they will find a way to get it done. And if not, they will find out like why it shouldn't be done. And they love progress over perfection, which I think a lot of times in the industry it's needed. And that you show some progress. And JPL being an applied research agency, we don't always care about progress. Sometimes we do care about perfection, but I feel like we have a pretty good balance because we are not core research all the time. So yeah, thank you. It was great talking, and I'll shut up now and resume and give the mic back to the organizers. Thank you.
Thank you so much, Asitang. Thank you for that, especially the last part. I was busy trying to, relate people we meet in the real world also, who can be divided into those categories. And I especially love the first and the last. Thank you so much for that lovely talk.
Thank you for that lovely talk, Asitang. I think we'll just take a bunch of little questions that the audience has proposed. But first, something that interested me way back for your stuff on the dark web. Now, if there's and Harshita from our team also asked the same question, that what is the big difference in terms of content between the sort of visible web and the dark web? Is there a sort of clearly big difference in terms of information type that one can point to, either through metadata or a descriptor or something like that? So if you had to tell a big difference, what is that? And why does one type of site get indexed over another type of site?
Yeah. So I think in terms of how it looks and like the kind of data, I don't think there's a big difference, to be honest. And I mean, if you count the Tor network, obviously there's a separate type of network, so that's considered part of the deep and sometimes the dark web. So that's a bit different in its technology itself, and probably the way the pages look and stuff like that. But for, I think most of it, it looks exactly the same. Let's just say that. The only difference would be I think if in your day-to-day life, if you're not seeing that page, if you're not able to use like go that deep into the web, then you basically categorize it as the deep web versus something that Google basically shows you. So why Google would show you, or why Bing or some other search engine would show you one page versus another, I think the reason could be many. There's obviously one is the commercial reasons why some sites are. I mean, I think the footfall of on a site is a big reason. While a lot of people would love to use very general type of websites, some people would love to like. I think it's whereas other people would probably not want, like, I think it's just a kind of ranking that depends on how many people, or I think it's kind of a democracy, right? Like if more people use a particular type of site, if more people are interested in a particular type of topic, then you would see those sites popping up more, like maybe sports and things like that. But suppose there's a rare type of sports somewhere being played in the world, the website for that probably would be only known to the people of that region or something like that, if it's not, obviously, if it's not gone viral. So there could be a lot of reason, I think, but the focus itself is a big reason, I feel, of what in general the population of the world is focusing on. Those sites would be usually on the top, whereas the sites which are mostly neglected, you don't even know they exist, but like a small community of people are running it. So that would be kind of much lower in the deep dark deep web. And if someone is doing an illegal thing in that as well, so I think it would be in their favor to actually keep it more hidden, not share the links with the. So you only get the link for that website, and you're not really putting the links to your website into all the public web, like you're not like really openly sharing it. So it's kind of disconnected from the whole graph of the internet. So those sites could also have their own existence somewhere. Sorry for the long
And
answer.
so, no, not at all. And how does that lead to a difference between the browsers themselves? Let's say sort of, the Tor browser and the MEMEX browser.
So so the whole project was also kind of a study of the same questions you're asking me. We had less idea when we started. We didn't know that those were the difference. We were like, oh, how these things would look like, we don't know. The difference is so it's not a browser. It's a search engine. So it's basically like that's a MEMEX search engine, basically. So what we would call it is like a domain specific search engine. So if you give it a domain, like if you give it a domain like cryptocurrency, then it would create a search engine for you around that domain of cryptocurrency. So it would go to the internet, it would scrape those pages in a very focused manner, it would organize that data, and then it would basically, so that you can search now that data, and it would be everything about crypto. Now, you would say, okay, Google can also do that, right? But Google has limits. It will show you maybe 100 pages, maybe 200 pages. What if you want to do an analysis on your own on, say, 1 million pages? Then you can't really do it on Google. So that's basically to have a larger amount of control of the research or the kind of search you're doing, because Google is kind of a black box in terms of you cannot tweak Google too much, their algorithm. You cannot say how much data it shows you, what it filters out. So if you want to kind of really search the internet on your own, you have to, I guess, build something of your own. So that was the idea, to kind of, if you build something of your own at such a large scale and a commercial level, what are the challenges that you face? Maybe Google had faced those challenges a while back while doing that, but the government agencies never had built a search engine before. You have to understand that. And so we were also facing those challenges anew, but our focus was to kind of do this search engine in a more domain-driven way.
No, that's lovely. And a somewhat controversial question, which I will also answer after you answer. Why did you choose USC over, let's say, one of the IITs for a master's?
Yeah, it is a very controversial question. So I think I heard long time ago the guy who was the founder of the Sun microsystem. He said that my son couldn't get into IITs, so he went to MIT.
Which, by the way, is a very glib way of answering. I mean, it's an insincere way of answering that question.
Yeah,
right?
I was not answering, but I was just saying.
No, I'm saying that Khosla's remark was glib.
Oh, yeah, it makes me chuckle because I did try for IIT. I remember it was a difficult time. Like no one can, I think, take away that IIT is the toughest engineering exam to get into. And I think that kind of answers the question, to be honest, is that I felt like, let's say it was a kind of an easier way for me to have prepared for IITs and versus I prepared for GRE. I felt like GREs were definitely much more my cup of tea because it was, again, boils down to English. I was very interested in English, and I think the GRE English was kind of a difficult one. So I was like, yeah, I can do this kind of English. I love this kind of analytics. So it's kind of more straightforward for me to do that. So I think that was definitely one criteria of like one factor of like what to do. I think another would be, and this I think this is a very kind of serious one, is that I feel like American universities kind of get that kind of exposure that at least I wanted. I wanted that kind of opportunity, the kind of research money that American university gets, and so I think it was the research attracted me. India, I feel like I always feel that it would be great if more research money is poured into not just IITs but more and more colleges in India. And also I feel like if there were more IITs, for example, compared to how many people want to study at IITs in India, then I would have probably gone for an Indian IIT or NIT or something like that instead of going for an American university.
And I'd like to add to that, like somewhat, let's say a little provocatively, how many Indian professors does the crowd know here, right, by name?
Yeah.
And there is something called, so American academics occupies a very central and prominent place in the American way of life, right, which makes especially their graduate school system, just absolutely outstanding. It's really hard to point out, also because it's been 25 years since I went to MIT. But even in the American academic system, let's say outside of Caltech, which Asitang probably knows well, there is no equal to MIT, like in the technical field, right? And it seems like slightly a loose statement to make. But once you go there, you realize that like literally every 15 feet that you walk, there is something or the other that's potentially world-changing going on, right? The US university is almost not at all about the teaching. It's almost entirely about research, right? So that's number one. The second is, and obviously it happens because there's so much government funding. Imagine something like JPL in India. Yeah, I think certain movements are in place which may make certain things like that happen in India, but we don't have anything close. Right? The second is the academic system. The system doesn't actually teach you; it forces you to learn yourself. Right. So I'll just give you an example. The average class in a good US graduate school probably gives you 300 pages of material to read and not from a single book. Right. So a professor expects you to walk into a single lecture of 1.5 hours, having not only mastered your text, whatever the recommended textbooks are, but also all the context around it, that you need to be well informed and need to be able to quickly parse information and then have a conversation with your instructor about this, right? So completely the opposite of what we have here. So if you successfully pass through a US education system, you are at the very least a phenomenal information gatherer and problem solver, right? And so it's a combination of multiple things. I think so far we as a country haven't taken our academic system anywhere close, and we should. And by the way, incidentally, one of the reasons why we built Univ.AI is that to bring that kind of a system to people who are interested in learning. So we're not very, guaranteed jobs, this, that, and the other. But if you understand that great jobs come to people who are extremely good at what they do, we are interested in those people. I'm interested in those people. So that's why we created this. So
I entirely agree with what you said.
So thanks, Asitang. Thanks a lot. Glad to have you here. And I think it's time to get on to our next one.
Thank you.
Which, ironically, is me.
Yes.